Okay, let's start. Today we will cover as much as possible about module and bimodule categories. This is chapter 3. But before starting, I have two small additions for which there was no time yesterday. But first of all, I have drawn here the definition of the Hopf algebra structure of this coend, assuming that it exists. One good aspect of coends is that they come with this natural family of morphisms, which I call I. And from the very definition, it follows that the morphism with codomain L is already completely determined if you give the corresponding morphisms, that morphism composed with all these I-axes. And the I-axes are part of the structure, so they are given. So so this here really defines what the coproduct on L is, because we know what this is and what this is. And analogously, co-unit, unit, product, and antipode. And notice that for the algebra structure, we need the braiding, but for the co-algebra structure, we don't. So that is valid more general.
So early, you define the algebras object in the general model.
Yes. So this is this is a category which, in order that all this is defined, has to be braided and rigid, and the coend has to exist. So an example of a large class of such categories are finite tensor categories, but it's valid beyond those.
So here this notion of algebra object,
Yes.
it's not always representable as a usual of algebra.
Well, if we specialize this to the category vector spaces, then we get an ordinary algebra.
Otherwise, something new. Otherwise, it's something new. Also, if you are not in vec, what you get is something new.
Well, it's a structure that exists there that you can define, and there are examples. For example, if we take C equals H mod, where H is a K algebra with suitable properties such that all this is, these things exist, then in fact L is as a vector space H star, and as a module, it's what is called a co-regular module. And this is a nice example of a class of categories where you know this very precisely. In general, you only have the definition as a coend, and this is not very explicit. So it can be hard to work with these things, but the important ingredient is always that you can use this linear family. And the second comment is I introduced the notion of modular fusion category, or more general modular tensor category. In a sense, not many of them are known. There are, of course, infinite classes, but very special infinite classes. So you have modular tensor categories associated to a pair consisting of a semi-simple Lie algebra and an integer for each simple sum, non-negative integer, and maybe I mentioned here that this would be C, G, K, L, say for G simple, otherwise there are several L's. And let me mention the book of cuts, where you find the modular data for that, and also the Etchinghoff et al. Book 8.18.2 for the case of G equals SL2. And then you have, whenever you have a finite abelian group, maybe I should call it G, in the USA, and a non-degenerate quadratic form on it, then again you can associate to this modular fusion category, and in this case this is example 8.13.5 in Ettinghoff et al. And then I think that I mentioned that well, I did mention that dg mod is the for G a finite group is the same as the Drinfeld center of G mod, and it turns out that this is actually modular. And then an example for non-semi-simple modular tensor categories is the representation category of, let me call it WP. This is a vertex operator algebra which corresponds to a certain class of the Xorian models. And let me mention here Tria Wood. That also I should mention. These are very closely related to constructions which use so-called Nichols algebras, which are a particular class of Hopper algebras, and that you find in a paper by Lentner. That is not yet in the reference list, but it will be added. And a subclass of those correspond to what is called symplectic fermion models, and about those you will find something. So now let's start with chapter 3. We have talked about in chapter 2 about monoidal categories. These can be regarded as categorification of the notion of a ring, and analogously you can categorify the notion of a module over the ring in the notion of module category. And generally in categorification, when you start with something where there is a property like associativity or commutativity, then this is turned into structure, like associated monoidal categories and the gradient for gradient monoidal categories. And now let me give the definition very briefly. A left module category over a monoidal category C is tuple consisting of a category M, a functor, sometimes called the action functor, which is from C times M to M, and then two natural transformations A and U associated to it, where well, U is an isomorphism from one acting on the identity functor of M to the identity functor, and A is natural isomorphism from first tensoring in C times the identity on M, and then acting to first acting and then acting again. So these are functors from C cross M to M. And so this is just analog to the associator and this to the unit of a monoidal category, such that a pentagon diagram and a triangle diagram commute. And I will not fully write out them. Well, maybe I write all the objects. So U, V, W are in C and M is in M. And so from here to here, I get via this module associator or module constraint. Here I can go to via the associator of the of C. So here I take the associator inside the bracket here, acting on M. I don't write the label. And here I have again the module constraint to go to U tensor, V tensor, W acting on M. And here the unique morphism type the identity on U and then the module constraint here and the discommutes and triangle V tensor 1 acting on M. We can use the module constraint to change the order. Or we can use the uniter of C to go to V acting on M. And here we can use identity on V times the unit constraint that we have for the module. And analogously, I don't write this down. You have a right module category. As I already said, this functor that we have here is often called the action functor, but the same name is also used for the functors where I fix either the first argument or the second. So these are functors either from M to M or from C to M. Also, they are called action functors, so one has to be careful when one reads the term. And the natural transformation here is called the module constraint or module functor constraint. Abbreviate this. And the pentagon, or sometimes also called a mixed pentagon, because it has both the associator of C and the module constraint of M. Then once I have left and right modules, I can define bimodules. Instead of module category, I will often just say module. Save time. So, assume that C and D be monoidal categories. And then we say bimodule category or CD bimodule category is a tuple consisting of the category M, then an action functor with corresponding constraints such that these together give a left module category, a left C module category, and a right action functor with corresponding module constraint and unit constraint, such that together with M, these give a right D module and another natural transformation A with this symbol here, which has components I don't write components. It exchanges the order of acting left and right. Either we first act from the right with D and then act from the left with C, or the other way around. And in this case, we have two pentagons, two additional. So we have all the two pentagons and two triangles for the module category part, and then we have two additional pentagons, which one of which looks as follows: U tensor C, V acting from the left of M, and then acting with X from the right. So U is in U and V in C, and X is in D, and M is in M. And then we can take the module constraint for the left action times the identity to get to U acting on V acting on M, and then acting from the right with X. We can use again we can use the mixed constraint here to go from here to U acting on V acting on M acted on by X, and then we can take the identity on U together with again the mixed constraint to get to U acting on V acting on M acted on by X, and here we can use the mixed constraint to get this to U tensor over C V acting on M acting on X, and then you have something here. And then there is a second pentagon, which I don't write down. This would be an exercise to fill in the full labels here. And the other pentagon is where you have one object of C and two objects of B. And then let me mention that if the categories are linear, as usually also normally assume that that also M will be linear. So C is linear, we take M to be linear, and then have linearity of those various structural morphisms. And there is a problem with this definition. It's somehow too general. You can give module categories which are very hard to treat, and if you try to classify them for a category which is too complicated, it can be extremely hard. And therefore, there is a second version of particular version of the definition, which I will mainly use in the following. And in this case, we assume that C is a finite tensor category. And then all this, what I have written here is still correct, but we require in addition that the category M is locally finite K-linear abelian category. And then this is, you find in the Eppinghoff book as definition 731. If M is not just locally finite, but in fact finite, then one talks about a finite module. Oh, I forgot. Important part. I not only require something for the category, but also for the action functor. I require that this functor has, well, it's bilinear on morphisms. That I already said. I will always require such things, but also and is exact in the first variable. Meaning that if we fix the second variable, like here, then for any choice of M, this functor here is exact. Actually, it follows, one can show this with another exercise, that the action functor with this definition is then automatically also exact in the second variable. So also these functors here are all exact. Now, in what I will do in the following, I think always all categories will at least be additive, and I will not say this explicitly. Very often we talk about finite tensor categories or similar categories, and this is anyhow automatic, but at least additive I require in any case. Now, this is still too general for many purposes. In order to get good results, one has a further restriction. This is, if I don't write in where you find this, then it's always the Eppinghoff book. It's definition 751. An exact module category over a finite tensor category C is a C module in the sense of this definition 3.5, such that for every projective object in C, and any object M in M, so I should give this a name M here. Also, the object E acting on M is projective. Was in M. It's already section 3.1. I haven't introduced, it would be definition. Now we have a section 3.2, which is examples. Just to mention a few. In general, still having the right notions, it's hard to classify module categories and bimodule categories. One aspect is that one really classifies what is called indecomposable module categories, a notion that I will be able to define only a bit later, but you can imagine what it is. So every module category is not indecomposable, is a direct sum in the simple sense of indecomposable ones. And there is and so one typically only tells what the indecomposables are. But there is one generic example. This is the regular module or bimodule, left, right, or bimodule. In this case, M is just C itself, and the action respectively, the left action, respectively, the right action, are just the tensor product. And of course, then the constraints here are the associator and universal of the category C, and the additional as an additional constraint we have for bimodules is again the associator of C. So there is. I should mention, I haven't written this here. There are also other generic examples, but for very specific types of situations, like if you not look at a single category, monoid category C, but the linear product of two or several of them, then there are naturally module categories over this which are related to permutation. These are also called permutation modules. Another example. Okay. Let's take G-graded vector spaces, where G is a finite group. In this case, the indecomposable C modules are classified by pairs H, omega, where H is a subgroup of G, and omega is a true cohomology class. Values. This is over C. If K is in bad characteristic, then it becomes more complicated. This actually generalizes to these twisted, these categories were twisted associated by a 3-cocycle. Psi, in this case, one has to require that the 3-cocycle is the identity on the subgroup H. And one way to explain this is I have actually given you a classification of algebras in those categories which are classified in a similar way. And then by result that I will mention later, the category of modules over those algebras is a module category. And if you have Morita equivalent algebras, more or less by definition, they give the same module category. And this results you find at many places. Like I've written it here, but in particular, the second paper by Ostrich gives you this information. This I have here, example 2.1. Yeah. And there's more in that paper to which I will come now, namely, if you're more interesting, is the situation that C is the Greenfeld center of the category. In this case, again, you have pairs H omega, where now H is a subgroup of G cross G. And we have psi tilde restricted to H is equal to 1, where psi tilde is the 3 cocycle on G cross on H. The 3 cocycle on G, which I get from the one. 3 cocycle on G cross C, which I get from the one on G by putting it back to the first and second factor here and actually subtracting it. So, but you find the details in that in that paper. And again, omega is such second cohomology class. Then let me mention that in this in the situation there, H is a K of algebra, finite dimensional, important. Then this always has vector spaces, finite dimensional ones. Maybe I write it explicitly. As a module, then this is a module category over H mod. And then, as I already said in words, assume that A nu eta is an algebra in C. Then mod A right modules is the C module. When I say C module, I typically mean left module. So from right modules over A, I get a C left module. And this is simply by saying that X in C acts on A module, which corresponds to an object M dot and a representation morphism rho to be just a tensor product in C of X with M dots, and then the identity on X tensor with the representation morphism. So X is just a spectator in a sense. And using this, you can use this here. Also, you get, for example, the module categories over these category C G of K. For example, when G is SL2, you get the ADE classification of module categories. Let me mention in words some applications. Only write a little bit about this. There is a notion of pivotal module category, which I don't have time to explain. it's a structure on a module category which is suitably compatible with it's over pivotal monoid category, and you find more about this in the third paper by Shimizu that is in the reference list. And the such categories describe boundary conditions. In three-dimensional Toral zero type topological field theories, and find this, for example, in this paper here. Then, if you have a modular tensor, modular fusion category, well, more generally, a modular tensor category captures aspects of what is called a chiral, aspects of chiral two-dimensional conformal field theory, and then let's call this C, and the pair Cm, where M is a suitable module category over C describes what is called a full conformal field theory, which has the chiral conformal field theory based on C, which corresponds to the chiral conformal field theory, and we'll say more about this next week. But mentioned already that there is a review where you find this and more information. And finally, if C is fusion, then from C and M you can. These are main ingredients in what is called the fusion 2 category, which in turn is used in the construction of certain four-dimensional conformal topological field theories, and this you find in Laplace-Reuter, which is not yet in the list, so it has to be added. And then once we have module categories, we should also talk about module functors. And this is expected. So I will not say too much about it, but I want to mention also module profunctors. Definition. An obflux module functor between left C modules M and M prime is a tuple consisting of a functor, call it F, from M to M prime, and a natural isomorphism family by xm from F, x acting on M in C to x in M, the action for M to the action for D, maybe I indicate for M prime, and F of M. Maybe I write a prime here. And such that a pentagon is commutes, and let me only indicate some parts of the diagram, and the rest is then exercise to fill in. You can use phi to get here to x tensor y acting prime acting on f of m, but you can also use f of the module constraint to get to f of x acting on y acting on m, and then you have two ways here to get to x acting on y acting on f of m. And the triangle f of 1 acting on m using phi, you can get to 1 acting prime on f of m. And from these two, there is one interesting way to get to f of m, and this is to commute. And only important thing here is that when I say oplux, I have these morphisms in one direction. They need not be isomorphisms. There's another notion of flux module functor, where instead you have a morphism the other direction, and then you have pentagons and triangle where the direction of the arrows is reversed. And then functor is both lux and oplux in such a way that you have isomorphisms, and then you call this a strong module functor. And if you're only interested in strong ones, then one just say module functors. Even if the module functor is strong, it need not admit joints. That is an interesting side remark. And now I can define what indecomposable means, namely we say that C modules M and M prime are equivalent if there exists a strong module functor such that the underlying functor is an equivalence of categories. And then we say that a direct sum of two module categories, let's say M plus M prime, of module categories M and M prime, this is the Cartesian product of them as categories with, and then just the only sensible way on defining a module structure on the Cartesian product. So component-wise, or some people call this coordinate-wise, and then an indecomposable module is a C module that cannot be written as a non-trivial direct sum of modules. Non-trivial means, of course, the zero category is already with everything being zero is a module category, and M can be written as a direct sum of itself, and that we want to exclude here. By the way, also 314, a definition, an indecomposable algebra. In a monoidal category C is a category for which the category of A modules is indecomposable as a module category. So one does not define this directly for algebras, but uses the definition. And my time is over. So let's have a break and then continue. So I mentioned that I also want to define module co-functors, and this will be very brief, but I do it mainly to explain why profunctors and therefore also module profunctors are important. Let's call it, well, I call it H here because it's called like that in some paper. So we have a C module M, I don't write this explicitly, and a C module N, and then we use this notation for profunctors. So this is, we assume here that C is linear, then we require that it's a bilinear functor, which I call again H, which goes from, what is my convention, M opposite times N to vector spaces. There is also a nonlinear version where I have instead a set here together with the family I call theta, M and X for M and N in M and N respectively, and X and C, which goes from H of Mn to a vector space, to the vector space H of X acting on M, X acting on N, which is natural in M in M and in N in N, and denatural in X. And it respects the tensor product and the unit. So M N, if I take a tensor product for the argument in C, then this can be written as the composition of Y acting on M, Y acting on N, and X with M and X. And compatibility with the unit, if C is in C, we take the tensor unit, then we just get the identity. And there's also the notion of morphisms between module profunctors, which are just natural transformations which are compatible all the structures. And generally, it's nice to deal with pro-functors instead of functors in situations where one starts with a category which turns out not to be large enough, and one has to do a certain completion. And sometimes well, when I talked about pro-functors, I said a little bit about Cauchy completion. Sometimes it's hard to describe those or work with those completions directly, but instead you can work with pro-functors for the original categories. And the same is true when you deal with module functors and then module pro-functors. And there's one result that I want to mention due to Shimizu. This is the third in the again in the papers by him that you find in the list. So there is, he says there's a canonical bijection between oblux module functor structures on a functor f from M to N, and C module, I don't write C module pro-functor structures on the functor Hom N F here. So this is this has a natural structure of a pro-functor from N to N, and similarly of Lux module functor structures on a functor G, say from N to M, and module pro-functor structures on M, and then the functor in the other argument inserted. And I have chosen here exchanges N and M, so that in both cases I get a pro-functor of this type. And you can combine these to relate Lux functor module functor structures and oblux module functor structures on a given functor. And another definition which I almost had forgotten, therefore it has a separate. No, actually I left out 17, so take this number. We assume that M is an exact, the way I define C, and I use A now for the monoidal category. Then one sets A M star to be the functor category in the case I'm considering here. In more general cases, one might consider only left or right exact functors from M to M, which are module functors. I indicate this by the label A here. So A module N functors. And this turns out to have many interesting properties. You can find this in the Ettinghoff book in chapter 712. Let me just mention a few of them. So AM star, if we take C to be a finite A to be a finite tensor category, then AM star is in general a finite multi-tensor category. And Well, it's the monoidal structure is just a composition of functors, and the duals are given by left and right adjoints of functors. And moreover, if M is indecomposable, then AM star is in fact the finite tensor category, not just multi-tensor. And also via just acting, defining the action as of a functor to an object here on an object in M by just applying the functor to M, which I can do by definition. Then AM star is not just the left A module category, but also no, sorry, M is not just a left A module category, but also a right AM star module category. And these fit together into a binomial. And more generally, you can, instead of these functor categories, consider the categories functors from module functors from M to N, where M and N are module categories. This is naturally A M star. Let me see, is this correct? No. Should be N. A N star, A M star module category. And you find more properties in this part of the book. Now, an important tool for working with module categories is the structure of an internal HOM. And there is a dual version, internal cohom. And one gets to this by simply noticing that the tensor product is an important functor, and then it's natural to ask what are left and right adjoints of it. And then one has the following definition. We take to C to be a k-linear monoidal category. And then very often we are interested in finite tensor categories actually. And then we say that for two objects Y and Z in C, the internal HOM, which I denote by HOM with an underline from Y to Z, is an object that represents the functor from C opposite to vector spaces, which sends an arbitrary object X in C, in COP, to the morphism space between X tensor Y and Z. And if you remember what it means representing, you can write this in terms of morphism space from X to something. That means we have natural isomorphisms between the morphisms from X tensor Y to Z, and the morphisms from X to this object internal home of Y and Z. And it's called internal home because if you specify this to specialize this to the category of vector spaces, then you just get the ordinary home function. And this also tells you that a home functor is right adjoint to the tensor product. And let me just mention that sometimes one calls this also the right internal home because one takes the right factor in the tensor product here. There's a corresponding left internal home, which is still a right adjoint. So in that case, you have Y here and you have X on this side. The necessary condition, in general, of course, internal homes need not exist. The necessary condition is that the tensor product is right at exact. But as I mentioned some time ago, under very mild conditions, the tensor product non-category is right exact. Actually, I have tried to find a precise condition for that, and probably they are so obvious, but not to me, that nobody cares about writing up precisely. In case anybody of you knows, please let me know. It is, of course, right exact for many concrete categories like representation categories of algebra and so on. Analogously, there's a notion of internal cohom, which is not the right adjoint, but a left adjoint. So let me just write the corresponding adjunction on X and Y tensor. Now we have the tensor product on the right, so that we can get the left adjoint, which we then call the internal cohom of. Now I have to be careful that X and Y, where this would correspond to the right internal cohom, and again there is a because I have taken a set to the left hand side, and there's a corresponding left internal cohom. This generalizes directly from monoidal categories to module categories. Then we are at definition 23. So in that case, we will have now not objects in C, but in M. Let's call them M and M prime. So this will let me just write down the corresponding junction. We have now an action here, and then the two variables here have different meanings. So there's only one internal home, and then analogously we have. Now I have to be careful. This is now morphism space in M, and here I have morphism space in C. And analogously for the internal cohom, and here I choose to start with X with M prime, and then X acting on M, and then I have here M prime and X. what I said about that there is only one internal Hom was nonsense. Because you can still, let me see, no, I think it's good. Now, if you can ask, is the internal cohom indeed necessary to talk about? If you look in the literature, you will not see it as often as the internal Hom. And the reason for that is in the literature, most often C is taken to be rigid. And in this case, the internal cohom is nothing new. It's just the left dual of an internal Hom. Also, you might have noticed that I have said the internal Homs, we only require it to be an adjoint, right or left, depending on Hom or cohom, which is not unique, but it's unique up to unique isomorphism, and therefore it makes sense to talk about the internal Hom and cohom. But sometimes one has to be careful in keeping the relevant isomorphisms talked about in several different contexts. And well, then here I have defined this. This should now be M and M for two fixed objects, but you can. Oh, I'm fine. But you can take them as variables, and then indeed you get a functor from M op times M to C. But you get the action of the functor on objects and a morphism is easy to deduce. Then there are some interesting further properties. One of them is that if I look at the internal Hom, write one, so I don't write that from now on, where I act with X in C on one of the variables, then I can take this out of the Hom and get a tensor product with it. And analogously, if you have it on the other, in the contravariant argument, then you can take it out to the right side, but it becomes a dual. And for the cohom, analogously, well, it looks the same for if you have it on the second argument. And if you have it in the first argument, you can guess what happens. You get again a dual, but now it's a left dual. And then the crucial property is the following. Let C now specifically be a finite multi-tensor category. M a C module and take an object in it. then the internal end, so internal Hom from M itself, comes with a canonical structure of an algebra in C, and also the internal cohom with a structure of a co-algebra. But since this is finite tensor, since we have a duality, this is automatic. So this is not a separate result really. And then if you take another object M in the module category, then the internal Hom from M to M prime is canonically or comes canonically with the structure of the left module over this algebra. And analogously as a left co-module over the in the case of the cohom. And much more about that you find in chapter 7-9 of the meeting. So now there is, I had originally planned to mention that Eilenberg-Watts calculus has a version for module categories, but there is no time to do that. So I prefer instead, well, let me just say that it exists, and let me just mention that there is a paper by Christoph Schweigert and Gregor Schaumann and myself, which you find in the list, and it's section 4 in that paper, I think. Yeah.
So, in the case of you take C to be the
Right.
internal Hom is just taking X tensor X star between the Hom of 1 and 1.
Yes.
Is there a notion of cyclic module where every object is united by a single? Then we can also.
There is notion of modules which have what is called a seed generator, which is precisely that they contain an object such that, to be precise, for all for any other object M, say an object M0, such that for any object M there is and now let me see. There exists an X such that there is an epimorphism to M, or there is a monomorphism in that direction. In one case, you call this, let me see. Yeah, I think here you call this a generator, and the other case quotient. And that's actually a structure which becomes relevant in what would be one of the next sections in the course if I had more time. But the first part of that is what I come now to, and this is Grothendieck-Verdier duality. This is a structure on categories which actually was studied much longer or much earlier than the name. The name is still Polyashchenko and Schönfeld, and this is the main reference here. And another reference, which I will not mention all the time, and then is by those authors and Simon Wood. And originally they were called star autonomous categories, started by Barr in particular, but in a somewhat more restricted context than I will do. On the other hand, my context is restricted in some other respects in the main applications. In order to save time in writing, I will just call this a G, V duality and then GV categories. This is a generalization of rigid structures, and you could ask why does one wants to have that? One motivation comes from classical algebra, namely, if you take an K algebra A and consider A bimod, finite dimensional, I will write this as usual, modules over finite dimensional K algebra. Maybe I write it once here, but no longer. And then this category turns out in general for general algebra not to be rigid. This is not hard to see. I'm just looking at an example. First, remember from corollary 279 that if C is rigid, then the functors of tensoring with a given object X from the left and the right are exact. And I just give you an example of a situation where such a functor is not exact and therefore the category cannot be rigid. It's maybe the simplest algebra one might think of, where something like that can go on. Just some people call this the dual numbers. So just a two-dimensional algebra polynomial in X of degree 0, 1, modulo X squared. And this has a canonical basis 1x, where by this mean the class is modulo X squared, but I don't write that out. And then this turns out to have 2 up to isomorphism in decomposable modules. First of all, A itself, which is projective and two-dimensional, and S, which is simple and one-dimensional, from which it directly follows that P actually is an extension of S by itself. So there's an exact sequence, a Claude exact sequence of this type. And this means in particular that you have here a morphism phi, which has to be a monomorphism. And it turns out if you apply tensoring, I forgot one thing, tensoring with S to this. I said bimodules here, but I'm talking about modules here, but this is a commutative algebra. So every module is trivially a bimodule, also using the flip map. So if I apply this tensor here, then phi is mapped to the zero morphism, which is not particularly mono, and therefore this functor is not. So it's an exact sequence to one which is not exact, and therefore it cannot be exact. And actually, full details about this you find in an earlier paper by this, if you're interested. let's see. Turns out that for these categories A bimod, internal homs and cohoms exist, and let me just write for the right internal hom. This is just, it's now a vector space, and it's a vector space of A module morphisms from M to N, where M and M are bimodules, but here I mean module morphisms which are morphisms of right modules and indicate the right, indicate only that they are right actions. And it turns out that this can actually, maybe I should not start with them. I should start with the cohom for the reason that you will see. This is analogously the morphism space of, maybe in the one, for once I write this on the left. Now I'm talking about left modules. And then you can show that actually this space of left module morphisms is the same as the tensor product over A in the way we defined long ago of y, not y, of n and m star, where m star is a dual vector space with natural module structure, and here you get instead and then this other tensor product that I mentioned. So this is right exact, this is left exact, and similarly for the other internal hom and cohom. Now notice that this means in particular that I should write it here, but this would be the right one. For the left one gets analogously that this is a tensor product again of this type, where I take the dual of x, not x, and of y, of m and no, yeah, in the opposite direction, opposite order, and generally these two bimodules are not isomorphic. So generally, left and right internal cohoms are different. Now, looking at this example and at various other situations, one is led to the following definition. This is called the Avail. It uses first the following notion, dualizing object. In a monoidal category, this is an object which I will denote by K, such that for every object Y, the functor sending an object X to the morphism from X tensor Y to K is representable by some object which one then calls G of Y. I don't write this down because in addition, one requires that this defines a functor G. Maybe I'll do this in yellow because I will use From now on, letter G will no longer be a finite group, but always this particular morphism, this particular functor from C to C up to contravariant endofunctor, you could say, which is an anti-equivalence. With a family, natural family of isomorphisms, which I call omega, say, from these morphism spaces y x tensor y to k, and a morphism space where I have x, and then on the right hand side a g of y. And then coordinate category is a monoidal category C together with such a functor G. And G is also called the duality functor or coordinate duality. And one should keep in mind that in the definition of G we use K. So in principle, one should have a index K here, reminding us that the dualizing object that in such a category we always have a dualizing object here in these isomorphisms, and we have chosen one of them. And this is structure, and I say a little bit more about in what sense this is structure a bit later. Let me mention that here this involves only the action of the functor on objects. We also have to define it on morphisms, but it's actually uniquely defined if one uses also the unital lemma in a suitable way.
So GV category in the definition of GV category, there should be a triplet, right?
Is it GV category? Is a monoidal category?
I'm saying that your GV category equal to C comma G, there should be K also, right?
Right. I actually said that.
Oh,
So there is always K, but G depends on K. So we choose K, and then there is such a functor G, but we call it only G. Now there's one important result. The functor G turns out if we have a rigid duality, then the duality functor, left or right duality, is monoidal. So it's monoidal except that it goes to the opposite category. This is no longer true in general for G, but it is still true. This is in this Boyachenko-Dritfeld paper, for example, that the functor G squared, which is an endofunctor, is monoidal. And the proof is not complicated, but also not short. And the next important thing is, remember, in this motivating example, we were using this tensor product here, which is right exact, which corresponds to the tensor product in the monoidal category we're usually working with. But we also had a left exact tensor product. And it turns out that the definition here is made in such a way that you have a substitute or generalization of this also. And for this we define a functor which I call just a block or something. So this is another tensor product. In that paper here, we find a nice symbol, which I cannot draw. And in the literature, there are several different symbols for this. And some of them have advantages. And there is no, I do not know of a choice which really fits best. And we will see in a minute why, but after the break. So this is a functor from C to C, which on objects is given by sending X and Y, X and Y to what I get by taking G of Y, tensoring it with G of X, opposite order, and then using G inverse. And analogous morphisms that we mentioned right away, that instead of taking G inverse here and G here, one could do it in the other way, in the opposite order, opposite way. This gives another functor which is of interest, but it's not a new one. It's canonically isomorphic to this one because of this property here. And now you can ask, is this something new really? And one can show actually that if these two functors are isomorphic, then G is opmonoidal. And that means that C is actually rigid. So as soon as we have a non-rigid category, this is something. And then I wrote this first because it's quick, a bit more time, which I don't have, but let me use it anyway, is that this gives another monoidal structure on C, and I will denote it by, well, we have the same category, we have a new tensor product. It turns out the dualizing object K is the monoidal unit for the tensor product, and then we have unitas and associators for that, which actually can be easily expressed in terms of the unitas and associators. Of the other original tensor product structure. So A blob X, Y, Z is the same as A G of Z, G of Y, G of X inverse. Well, let me write a tensor here to be no, that's not yet correct. I have to apply G inverse. And with this and analogous formulas for the unitas, it's just a matter of direct checking that indeed these morphisms, these natural transformations together with this as a tensor even satisfy the pentagon and hexagon.
It's not rigid.
It's
This new monoidal category is not rigid.
no, if it's not new, then this is equivalent to being rigid. So if you have a rigid category, it could happen, for example, in the bimodule situation here, that the category is rigid. There are examples. In that case, these two tensor products are not equal, but isomorphic.
Yeah, he's asking, C is not rigid, we have a new category. And this new category, is it rigid?
No, it's not rigid. It's remember, rigid is a property, so you can say this is not rigid. there is no rigid structure on it. If it's, unless it's rigid, C is rigid from the outside. So yeah, if this category is not rigid, then this is also. Okay, so maybe last sentence before we take the break. And we have now two different tensor products, and we have arrived at this one by starting from the original one. But we could also have started from the left exact tensor product and just reversing everything and ending up with the right. So we should really take not this as some derived structure, but rather you have two different tensor products, and they should be treated on equal footing. And one comment in addition, which I haven't written down, there is a notion of duo-equal category, which is a category of two monoidal structures. This is not related to all this. Because someone has asked me about this. I forgot to provide you. Okay, let's stop here and then continue 10 past. So, the rest of the lecture today, I will say first more about Categorical, and there is much more to be said about them than what I can do here. And then I will say a few things about Frobenius algebras and monoidal categories, and a tiny bit about Frobenius algebras and Categorical. But let me first mention one property from the very definitions, it follows that this morphism space can also be write as a space of morphisms well, that this is isomorphic using the fact that that G squared is monoidal to this space, and also isomorphic to this space for all x, y, and z in C. And if you compare this to the isomorphisms you get from a left and right duality, you see that in this respect, G behaves like a rigid right duality and G inverse like a rigid left duality. And there's more to be said about that, but I'm not sure whether I will come to it. So therefore, I want to say this already now. And then there is the following proposition, again by Poyatchenko and Grinfeld, which tells in which sense the choice of dualizing object is structured. Namely, it says that G and also G inverse furnish an anti-equivalence between two full subcategories of C, namely the full subcategory of dualizing objects in the sense just defined, and the full subcategory of invertible objects. And also some other related statements. So, for example, if U is invertible, it follows that G of U is K tensor. So right exact tensor product times U inverse, and similarly for G inverse. And also, if U is invertible, then G squared of U is invertible. So G squared sends invertible objects to invertible objects. And this means then, in particular, that the dualizing objects for the tensor category with the other tensor product are the same as the invertible objects in bijection with the invertible objects of the with respect to the original tensor product and the other way around. Now, one important aspect of regarding the two tensor products to be on equal footing is that you should consider situations where both of them appear at the same time. And that means that when you have bracketings, when you have multiple tensor products, you have and want to change bracketings, you need analogs of other changes. And this is described by the following. From now on, we always talk about the Grothendieck-Verdier category C. I don't write this explicitly. There are natural families of isomorphisms of the following form. One I call delta R, x, y, z, from x blob y tensor z to x blob y tensor z. And one which I call delta L, x, y, z, from x tensor y blob z to x. I wrote this wrong, x tensor y blob z, and these are not isomorphisms, but they are morphisms in this direction, and they don't you normally have an inverse, and they satisfy six pentagon identities, which I don't write down because they are special cases of something I hopefully will be able to write down a bit later. Two of them involve only delta R, two involve only delta L, and two others involve both of them. And showing that the validity of these pentagons follows from the definition is actually hard. And the simplest way or the most the most conceptual way of showing it is actually in the way I will show it later. Well, the most conceptual way is known to me, and that involves the notion of Grothendieck-Verdier module categories, which is section 3.7. Let's just give you right away the definition. So C is a Grothendieck-Verdier category, and then we say that left Grothendieck-Verdier module category over C is left module category over C with the right exact tensor product. Let's call it M, and the action function as usual by this triangle, such that the functor functor of M, which I get from the action functor by fixing the variable in X, and the other one where I fix the variable in M, such that both of these have a right adjoint. Here for all x in C and here for all n in M. And just in words, notice that for this definition, we do actually not use that C is a non-invertible category. So you might ask, why do we do that? But it turns out this is the definition which fits in order to together with a non-invertible structure to give sensible results. And also, if in the case that C is a finite tensor category with respect to the original tensor product, then this definition reproduces the definition I gave for a module category or a finite tensor category. And in particular, this definition guarantees the existence of internal ROMs and co-ROMs. They are just the relevant joints. Let me just check. Yeah. Let me just give one example for these joints. You can take the regular C module. In this case, the right adjoint of this action functor turns out to be taking the G inverse of X and tensoring with the other tensor product. And I write this explicitly because implicitly in the few things that I will say is the following. When we talk about right adjoints, we make a choice. Unique up to unique isomorphism, but it's still a choice. In case that we deal with the regular module, we will always take precisely this functor as right adjoint. I should point here this functor as well. And then this is not one. There's the following proposition. Let us define a functor similar to the action. So if I take a pair XM, objects in C and in M, I send this to X dark acting or white acting here on the blackboard on M. This I write as H, G of X, H, G of X of M, where I use the following notation. I write in for general module the right adjoint of this action functor as Hx. And the right adjoint, now here I have to be careful. It's a right adjoint, so we make some fixed choice here once and forever, and then one can check that various results I will mention, or a few results that I will mention, actually depend on choice here only up to unique isomorphism, well, up to appropriate isomorphism. And then the proposition here says that this has left adjoint in each variable and defines a C block module category structure on M. So if I say a module with respect to this, then I require that the corresponding action functors have left adjoints rather than right adjoints. And that means whenever I have a GV module category with respect to the original tensor where in the definition I use the original tensor product, I also have a module category with respect to the other tensor. And then 16. Using this, one gets the following. We assume that M is left GV C module or C non-invertible category, and we take M with this action as defined, as just defined. Then M op is naturally the right GV C module and the right. So this is with respect to C and this tensor product, and the right C block module by the following definitions. Maybe I write it here. So we have to give a right action from M op cross C to M op. And this is simply that we send Mx to G inverse of X acting, but now acting with the other action here on M. And similarly, such an action, same type of functor, where we send Mx to G inverse of X acting with the tensor, with the direct tensor product, the direct action here on M.
So in 360, the C block module isn't GV module or regular?
Well, I have not really defined this. I just with this I mean the module category in the usual sense. With this tensor product.
Okay. But then, yeah. So I mean, what GV is a GV?
I could define a GV module with respect to that by changing things here, but it's doesn't give some new information, so we will not do that. And if I specialize this information if I use, it turns out that X acting in this way is right adjoint just by combining identities that we have seen to G of X acting in the other way. And using this, you can define evaluation and co-evaluation morphisms. Of which, when specialized to the case of the regular module category, give morphisms G of X for R morphisms G of X tensor X to K, and 1 to X block G of X. And this fits with what I said before about these isomorphisms. Once in the codomain, we use the block tensor product and use the unit for the block tensor product. We get a situation completely analogous to what we have for rigid dualities. And you can show that these morphisms that you get via this adjunction satisfy snake identities, which are analogous to snake identities for rigid duality. So surprisingly much you can do for rigid dualities, you can still do for polynomial dualities. And leave out a little bit, but I have to say something that is important about GV module functors and then module distributors. One can just define Lux and Oblux module functor structures in the same way as for an ordinary monoidal category. But now one has two versions, one for the one action and one for the other, and corresponding the two different tensor products. And it turns out that you have bijection between Lux module functor structures on a functor F between Grundliquidity module categories and Oblux module functor structures for the other. And more precisely, given such a structure here, you can construct such a structure. And given such a structure, you can construct such a structure. And if you iterate this, if you start here, come here, and do it again, you come back to where you started. So this, and this is very convenient for various proofs. And then in particular, this allows you to define analog of distributors for module categories. There's a right module distributor, which I denote again by delta R. Now it has X, Y, and M as labels, and goes from X blob Y acting on M to X black acting on Y acting, and a left one, left X, Y, M on X acting on Y, black acting on M to X tensor Y T acting. And it's in this direction, and this is in the case of the regular module category, it's just the distributors of that we have seen. But now the point is there, and I don't write anything about this because then we get to come to the next point. If you now, no, there is something missing here. This is not a definition. These are just some formulas. I have to tell you how we define them. This is defined by the Oplaks module functor structure on the functor which sends x to x originally acting on M. So this functor turns out, which is a module functor with respect to the original tensor product, turns out to be an Oplaks module functor with respect to the other tensor product. And once you have proven that, you just call the corresponding structure this delta R, and it is of this form by definition. And you have something analogous here, where you have use the Lux, this action module functor structure on the functor where you have the other action. And then, because module functor structures by definition obey pentagons, you get pentagons for these module distributors. And these pentagons, when you specialize them to the case of the regular module category, are precisely the pentagons that I mentioned before. And I don't have time to write them down, but you can easily find them in the paper I mentioned. Or actually, you can produce them yourself by just knowing that there will be two pentagons involving only this one. So there is indeed only one way to write a pentagon in a sensible way where you only use delta R's, and there is another one where you only use delta L's. And there are two of them, depending on whether you start with X blob, Y blob acting on Z, acting on M. This gives a pentagon, or you start with this. And analogously for the others. Now I have 20 minutes left for a final part here, which is a bit different in spirit from what I just did. I should mention that the part about Grothendieck-Verdier would have fit in section 2. I didn't talk about module categories in the first place, but it's natural to do it here in the context of module categories, just because you use Grothendieck-Verdier module categories in order to, for example, show the validity of the relevant pentagon diagrams. And next part, I could have started again in the section about monoidal categories, but at the end, I will come to a point for which I need some of the statements, well, a few of the statements about Grothendieck-Verdier categories. Some of the information. So this is called Frobenius algebras. And let me first start with a simple lemma. In what follows, A, mu, eta will always be an algebra in the monoidal category C. And then taking mu as left, respectively right, action of A on itself gives left or right, and then in fact bimodule structure on the object A. And this I call the regular bimodule. And now I use this fact in the definition of what is a Frobenius algebra in C. This is a quintuple A mu eta delta epsilon, such that A mu eta is an algebra, A delta epsilon is a co-algebra in C, and the co-products and co-unit are morphisms of A bimodules. And I could write this in a formula, but prefer to do it graphically. So the left action of A on itself is defined just to be the product. Therefore, when I say that this is a morphism of A bimodules, really means a morphism of left modules and of right modules. So acting, well, let me first draw it. So we acting first and then taking the co-product is the same as first having the co-product and then acting. And this is left action. If I take instead the right action, it will look like this. So all the lines are labeled by A. And you should compare this with definition of Hopf algebra. In that case, instead of a morphism of bimodules, we require a morphism of algebras. And also notice that this works in an arbitrary monoid category. For definition of Hopf algebra, we need a braiding. Let me also mention, and this is a nice exercise which I can only do graphically.
There's something wrong.
There's something wrong. No, it's correct, but it's correct in a trivial way. Better? But actually, this is what I wanted to say next. This equality, together with associativity, co-associativity, and unitality, co-unitality, is equivalent to this one. And this equal to this is also equivalent to that. And showing this is not completely trivial, but it's a nice exercise. Also, I should mention, this is implicit in many descriptions. I assume that the unit morphism is not the zero morphism. This excludes, for example, the strange case that I take the zero object to be an algebra. Because in some statements would no longer be true. One interesting result is that there is an equivalent characterization. Actually, if you look at this in the categorical vector spaces, then this is not a traditional definition of Frobenius algebra. The traditional definition is close to this one. Namely, it says that Frobenius algebra is the same as an algebra, A mu eta, together with an invariant non-degenerate pairing. call it kappa. So pairing means A tensor A to the tensor unit. And this is the same. That this is invariant means denote kappa, say in this way. So A tensor A to the invisible object. Then I require that. If I compose this with the product, it's the same as I compose it with the product on the other leg. And invariant means that there exists kind of inverse, so a morphism from 1 to A tensor A, such that this is the identity and this is the identity. And how do you prove this? Well, actually, assume we have a Frobenius algebra of this type defined in this way, then just define this pairing to be co-unit after product, and then you can check, well, the invariance is just associativity, and you can check that co-product of the unit satisfies these properties here simply due to the Frobenius property, due to these properties here. The other direction is more interesting. Let me mention it here. Define. So assume we have kappa and then also kappa, call this kappa bar. But I do it graphically. I don't need notation with it. Define delta 1 to be this morphism and epsilon 1. So we assume we have an algebra and have kappa bar to be this morphism, and define delta 2 to be instead. Wait, this is in kappa bar. These are morphisms which are in the right spaces for a co-multiplication and co-unit. And actually, we can take both of them because just by using associativity, you show that delta 1 is equal to delta 2 and epsilon 1 is equal to epsilon 2. And also, again, by not associativity, invariance and non-degeneracy here. And using associativity, we showed directly that you just have to draw it, that identity on A tensor delta 1 is composed with delta 2 is the same as delta 2 tensor with identity composed of delta 1. But delta 1 and delta 2 are equal, and therefore this says that delta is co-associative. And similarly, you show co-unit properties and Frobenius properties.
The definition kappa is.
Kappa is.
Kappa is given or it is.
Yes, here I assume that we have a Frobenius algebra defined in this way. So it's an algebra together with a kappa, such that I have these properties, and then I define. So I have a kappa and I have a kappa bar. No, we require that this is invariant. We require that this is invariant, so there exists some kappa bar with this property, and the other one, but it's unique, just like you inverses on it.
No, this is not generative.
Sorry?
This is not generative, not invariant.
What is not invariant?
This topology is non-degeneracy of kappa.
Yes.
The invariance of kappa is.
Yes. Did I say invariance? Sorry.
Yes. Yeah.
This is not degeneracy. This is invariance. To remarks which are nice, but which I will not write down, is that I mentioned when I introduced Lux and Oblux monoidal functors, the notion of Frobenius monoidal functor, which is Lux and Oblux, but they are not inverse. It turns out that if you have a Frobenius monoidal functor between C and D, and Frobenius algebra in C, then applying this functor to it, you get an Frobenius algebra in D. So these terminologies fit nicely together. Also, if an algebra, remember from lemma 244 that we have this induction functor giving us induced modules or free modules, and that this is left adjoint to the forgetful functor from modules to the category. If the category is, if the algebra is not just an algebra but a Frobenius algebra, then this is not only a left adjoint but also a right adjoint. And you can remember I showed the left adjointness graphically. There is a similar graphical proof for the right adjointness, but actually this boils down to the statement that if you have a module over Frobenius algebra, the Frobenius algebra is also a co-algebra, then the module is simultaneously a co-module over the co-algebra structure. And that is very easy to see. So if you have a module, so we have an action of A, then just use the co-product and the unit to define this morphism. So this goes from M to A tensor M, and this makes M into an A co-module, where A is regarded as a co-algebra. And once you have this, then you take the previous result about being left adjoint, you just reverse all arrows, you get a statement not about algebras but about co-algebras and about right adjoint. But then you use the fact that via this your co-modules and modules are essentially the same thing, and then you get this. And this is very important because being right adjoint is of course a very strong property for these functors. And now I write down another interesting statement. Proposition: every morphism of Frobenius algebras and I have not defined that. It's the following: it's just a morphism of algebras and at the same time a morphism of co-algebras. Nothing else. Every such morphism is an isomorphism. And I present here the proof because I find this nice. It's much quicker than one might expect. So we assume F from A to B. A and B are Frobenius algebras, and F is a Frobenius morphism. And what we need is a morphism from B to A, which is two-sided inverse to this one. And of course, it should be a morphism of Frobenius algebras. But that will be automatic. I just give you the inverse. Well, if I do not have any other information than F and A and B, how can I go? How can I get a morphism from B to A? Well, I need to come down with B, but there is one natural way, namely combining the product and the co-unit. And to get A up, I combine the co-product and the unit, and I claim this is an inverse. And to show this is actually very easy. Let's see that it's inverse from one side. If you put F here, and if you do it on the other side, it will be analogous. Now, F, now this, what I have here, I can redraw in this form. But F is by assumption a morphism in particular of the co-algebra structure. So this is the same thing as moving it through the co-product and having it here. But also it's a morphism of the algebra structure. Therefore, I can move it through the unit and then it's done. And then this by one of the Frobenius identities is the same as this morphism, which is identity. Oh, I'm out of time, but everyone who is already bored can leave the room. I want to say 2 words about Frobenius algebras in Bourdon-Verdier categories. Naively, you could say, well, Bourdon-Verdier category is monoidal, so just take over the definition, but it will not be something interesting. Well, it simply does not work in a nice way. Instead, we define a GV algebra in a Grothendieck-Verdier category C to be a C ordinary tensor product algebra, well, right exact tensor product, and a GV co-algebra to be a co-algebra with respect to the left exact. So we do not use the other possibilities. And then we say a GV Frobenius algebra A mu eta delta epsilon is, well, a GV algebra and GV co-algebra in the obvious way. Such that we have the following equality. And now this I do not draw for the simple reason there is no known or proven two-dimensional graphical calculus for Grothendieck-Verdier categories, even though there will exist something like that. But it will, to formulate it, you have to think quite a bit. So we have the following mu in our blob identity on A composed with identity on A tensor delta equals delta composed with mu equals identity of A tensor mu composed with delta tensor identity of A. So if you just would have this, then you would get these 2 equalities as before. But now you have to be careful. Say here, and we are on this side. You start with a tensor product, a right exact tensor product here, but here you have a left exact one. So at this point, you deal with first tensor here with blob and then tensor. No, you want that, that's what you have, but you want to have it the other way around in order to continue with product. And that means that you have to insert here a distributor, and it's just the left distributor for 3 copies of A, and here in the corresponding here right distributor. And if you now want to prove things here, one possible way is just take the corresponding graphical proofs for monoidal categories, insert distributors where they should be, and then prove the result. But you cannot prove the result graphically because, well, you get some idea on what it should be, but in order that it's a real proof, since there is no graphical calculus, you have to, in particular, it turns out at some point you have to use some of those pentagon identities, and it's hard to read off from the pictures which pentagon identity you have to use.
Where is the block tensor?
Here is block and here is tensor. Here is blob and here is tensor. Thank you. Two last statements. First of all, also here you have a definition, an equivalent definition in terms of non-degenerate invariant form, except that now we have to be careful. This goes from A tensor A, not to the tensor unit. That's not, it should not be so, but what comes out will be with respect to the block tensor product, so it will be the dualizing object. Also, we have this statement again about all morphisms of subtropious algebras are isomorphic. And then the final statement is that if you look in Ostrich's paper, the first of the two that is in the list, it tells you that you have, if you have a semi-simple rigid monoidal k-linear category, then and a semi-simple indecomposable module over that, then there exists an algebra such that the category of modules over that algebra is equivalent as a module category. And you actually get that algebra as an internal end. And in the Grundig-Verdier case, it's much more complicated. It's still true that if you have such an algebra, the category of modules will be a module category, but the other direction does not work directly. You have some conditions which are not very easy to formulate, which are not. Okay, that's it for this week. Next week will be rather different. I will probably use various things which I have not defined, but it will be applications, and I will use things that I have defined. So there is a connection, but first of all, several people have asked me whether I would come to some statements about conformal field theories and topological field theories, maybe essentially conformal. But then also in the original announcement I had talked about it. And I have completely misjudged the amount of time that is needed. Okay, please continue next week.
Motivation